Well, thanks everyone for coming out tonight. We're going to do this a little bit differently tonight. Dr. Edwards is here. She's going to give about 25 minutes-ish of presentation on her work, and then we will open it up to question and answer. Dr. Catherine Edwards is an associate professor in the Department of Marine Sciences at the University of Georgia, and her lab is based here at the UGA Skidaway Institute of Oceanography. She received her bachelor's in physics at the University of North Carolina, Chapel Hill, and she got her PhD in physical oceanography at UNC Chapel Hill as well.
Go Heels.
Much of her research includes what we'll talk about today, which involves sending autonomous underwater vehicles out to sea. Her lab uses these gliders to both monitor for critically endangered northern right whales and what we're going to talk about today, help hurricane forecasts. So please give a warm welcome to Dr. Catherine Edwards.
Hi, y'all. I'm so glad to be here tonight. And thank you, Jackson, for the introduction. Jackson asked me, do you want to do it in the old style format where you give, a 35-minute lecture and then take questions? Or do you want to do it in the new style format with like an interview and let's see how it goes? And I say, how about both? So that's why we're doing a little experimental thing. It'll be a little bit of both. So I'm going to be talking today about how we can use autonomous underwater vehicles and autonomous surface vehicles to improve our forecasts of tropical storms. And this isn't something like that is, some nebulous thing in the future that will have models better like in a few years or 5 years or 10 years. These are observations. This is work that improves our models in real time so that the forecasts we get from the National Hurricane Center tonight are better than they were this afternoon. So I'll start by acknowledging the large group of people I work with who do so much of this work. This is some of our current and recent staff members, technicians, and students who work in my group, some of whom are alums who stayed on, some of whom are Savannah natives that you might have met or have seen in some of our open lab nights and stuff. And then also as part of the introduction, our gliders, they all have names. So we have a Skidaway glider named Angus, named for the cattle who were raised on the farm that eventually became Skidaway Institute of Oceanography. Franklin, owned by Socorro, my funding agency, named for Benjamin Franklin, who was the first to have the Gulf Stream charted. Unit 1091, because we were in a hurry and we haven't come up with a good name yet, but she's going to get a name soon. Pelagia and Salacia are two older gliders. One of them is older than our summer intern, Dory Cook. And the other is about her age. And then we have a demo glider, Fodina, who is named after the prior glider, Modena. And if you live here on Skidaway Island, you probably know its source as the northern tip of the island. So gliders are autonomous underwater vehicles, meaning that they move completely on their own, or not quite completely on their own, but completely untethered, moving through the ocean by changing their buoyancy and center of gravity. Come on, friend, let's do it. Okay, there we go. So they move at the surface, they suck in a small volume of water that makes it heavier than the water around it and move a battery forward on a rail so it's tipped down. Then gravity pulls it down and the wings that are on each side give it lift for smooth flight. When it gets close to the bottom, it reverses the process. It pushes the water out so it's lighter than all of the water around it and moves the battery backwards so that it's pointed up. And then it can't help but for buoyancy to propel it toward the surface, flying horizontally. So it moves in that manner, moving up and down in a yo-yo pattern, measuring temperature, salinity, oxygen, chlorophyll, dissolved organic matter, currents, all kinds of acoustics like we use for the whales. And then the important part for all of this story is that it comes up to the surface every 4 hours and says, "Hi, my name is Angus. I'm in the ocean. This is my GPS position. This is what I've been doing. What would you like me to do? Would you like me to send you a subset of the data I've been collecting? Would you like to change my waypoints? Would you like to change my directions or something about how I'm flying? Or do you want me to go back down? And usually that's when all the pilots that I listed on that very first slide we'll give it a combination of those commands, sometimes to adapt its sampling in real time based on what we see in the data, definitely to get to the data because that's the most important part that we'll be talking about, and then send it on its way. I like to talk about this in terms of the jobs these gliders do, in terms of their impact. So we've got, is that Wayne calling in? Okay. In terms of their impact, we use them to study hurricanes. We use them to monitor endangered species. We use them to observe fisheries, habitat, and usage. But these are really examples of science for impact, not improving something in the future that maybe in 5 years I'll write a paper about. This is impact for the public every day. So first, I'll kind of introduce you to the hurricane intensity problem, which you probably have a pretty good idea of living on the coast and trying to decide when or where to evacuate. Then we'll talk about the hurricane glider program that we've developed over the last 8 or 10 years, and then look at some highlights and future plans. So this image here shows the National Hurricane Center official annual average track error. So over the time between 1970 through the present. And this is forecast error in nautical miles. Each of the colors represents how long the forecast is available. So a 24-hour forecast, a 48-hour forecast, or a 72-hour forecast. And starting in about 2000, we started to be able to predict longer out where the storm would be going. And you see over time, all of these errors are getting smaller. So we are getting better and better at predicting where the hurricane is going to go and predicting where it's going to go a longer time out than possible, giving us as much time as possible to plan. So if you can see visually what this improvement looks like, here's the path of a storm as it moves over warm ocean temperatures like we've got right now. The color represents how hot it is. And you can consider a 2020 cone or a 2026 cone right here. That same cone in 1990 would look like that. That same cone in 1970 would look like that. And so you would have a hard time distinguishing, even when the storm is off of Puerto Rico, like, is it going to go to the Gulf of Mexico or is it going to go to the Atlantic seaboard? So we're getting a lot better at that skill. But the big question is, how strong will it be when it gets there? And spoiler alert, that's the harder part to determine. So this is a plot that shows the same type of data from 1990 to 2024, but now we're looking at the forecast error and not. So this is the error in the speed or intensity of the hurricane. And you see that these slopes are flat, flat or improving very, very, very slowly. And we get more improvement farther out in time, but basically these errors still are 10 to 15 knots. 10 to 15 knots could be a full category or maybe on the edge of a category of the Saffir-Simpson scale, which is how we say a category 1, 2, 3, 4, 5. I also want to draw your attention to this. You see, like, this over the last, since 2022, these are multiple years in a row where we've been getting worse. What's the story with that? So let's take a closer look at that. And I'll introduce a term called rapid intensification. This error that happens appears to be driven by the phenomenon when a storm goes from a just okay storm to a monster. The formal definition is a change in wind speed of 30 knots in just 24 hours. So if you look at if you look at these same forecast errors and knots over time, when rapid intensification was observed or forecast, we are getting better. But this is still 20 to 30 knots. This is nearly twice as bad when rapid intensification happens. So what we're missing is these monster storms that blow up overnight because they're really hard to get right. And these 20 to 30 knot differences are potentially 2 to 3 categories on the Saffir-Simpson scale. So if you, like all of us who live here in this room, make decisions based on your evacuation zone, and however imperfect a Saffir-Simpson scale number is, it's what we've got. And it's how you make decisions to say, I'll stay for a 3, I'll evacuate for a 4, or I'll stay for a 1 and I'll evacuate for a 2. These differences can really matter. So what determines the speed, this intensity of a hurricane? And one of the primary fuels for hurricanes and their intensity is the heat within the ocean itself. That serves to fuel hurricanes and strengthen them. So the left-hand panel shows the tropical cyclone heat potential. You can just think about it as the integrated heat in the ocean over space. And so these red numbers are the red areas are where the hurricanes are likely to intensify rapidly. And that's not just at the surface, it's an integrated value. So it's at the surface, but finding out where that number dips to below 26 degrees Celsius. So it's this integrated heat in this upper part of the water column that matters. So if you have, for example, a glider that moves in the vertical sampling temperature, it is a near ideal vehicle for estimating this tropical cyclone heat potential. How much fuel is sitting in the ocean ready to help a storm explode through rapid intensification? So I'm part of a large project that has now become international to deploy our gliders into what we called essential ocean features. Where are the places that are most important for us to understand in terms of ocean heat content and in terms of the atmospheric variability above it? And that can help us understand where, when, and why tropical storms and hurricanes intensify. So this goes back to 2018 when we started the Hurricane Gliders program. This is when Hurricane Florence was taking aim at us in our area, and all the boats were coming in and we were going out. So we deployed one glider off of our coast and another one off of the North Carolina coast, and Hurricane Florence essentially bisected them. So here's a representation of how that helps. Because the data come back in real time, we can share that with the models that use it as a way to nudge the model closer to reality. So this shows temperature where it's really warm at the surface, almost 30 degrees Celsius, which is super toasty. And down at the bottom, it's much, much cooler, 15 degrees Celsius. And the green represents every measurement that the glider has taken, and the black represent its average. The Navy models that underpin the NOAA forecast models, without glider data, just have it be hot surface to bottom. They're missing that there's a difference, a gradient in that temperature. But when the glider data is assimilated, you more accurately capture the ocean heat content. And we were able to prove this in a real-time exercise that improved the Navy models in real time. So without the gliders, the hot water is all the way top to bottom, and you think there's more fuel for the hurricane. And with the gliders, you actually see that there's less fuel than you would think by just looking at the surface. Um, and this is more of a technical thing that shows all the many places that gliders come into the equation. We collect the data, we share it with these national and international databases that then get sucked up by our US NOAA and US Navy models. They get shared with the European models that you may look at when you get deep into hurricane season and start to have real feelings about each of the models. So we collect the data, we run the models, the weather and ocean models are run. We work with the National Hurricane Center and NOAA to analyze the data and the models. We provide weekly briefings to the Environmental Modeling Center, and we have storm response communication with the National Hurricane Center that ultimately results in the forecast that's issued to the communities. And this is a long time coming, and this is like nerding out operationally. If you've ever been kind of operationally minded, hurricane gliders are officially in the forecast system for hurricanes now. So we are part of the team. We started as a demonstration project, like doing things for free, volunteering, showing how useful we are, showing how easy we are. And then we have shown our worth. We are now part of the official process. So what does this look like? This is where our gliders were last summer, last hurricane season. From 2018 to 2025, we've done almost 60 glider missions, nearly 2,000 days in water, estimated 600,000 temperature and salinity profiles during hurricane season, and brought nearly $2 million to this effort since 2020. Nationally, you can see this is us here. This is from 2018 to 2023. Nationally, we're just one part of the picture. There are similar teams operating in the Gulf of Mexico, in the Mid-Atlantic Bight, and significant teams in the Caribbean. And over this time period, 74% of the named storms aimed at U.S. waters had gliders in their forecast cones. It's pretty cool. 8 out of 9, nearly 90% of major hurricanes had gliders aimed at the US, had gliders in their forecast cones. And we've had 68 in these 6 years, we had 68 glider intercepts over 25 named storms. So this is super highly successful. We are getting it right. We have found the right places to put our instruments. So this is just one part of a very much larger ecosystem. And with a little bit of time here at the end, I'll introduce you to kind of how we fit in. I grew up in New Orleans, Louisiana, and spent a lot of time on the Mississippi Gulf Coast, where the hurricane hunters operate out of Biloxi, Mississippi. I don't know if y'all have spent any time down that way. So you may be familiar with the hurricane hunters flying into storms, and I one day long to be on one of those planes. So the gliders are collecting data with the tropical cyclone heat potential. We also have these aircraft dropping dropsons. These are essentially temperature and humidity sensors that get dropped from planes. And there's little radio signals that radio back what the temperature and salinity or temperature and humidity profile is through the atmosphere. So you can observe, like in the movie Twister, the old version with the little robots that go through, you can see the structure as it drops through. We also have buoys operated by the National Data Buoy Center, drifters, floats, buoys that we can deploy into the storms, and then autonomous surface vehicles, sail drones, and ocean sea stars that I've been involved in these efforts as well. So all of these are being coordinated, collecting observations in coordination, in collaboration, advising the storm. So this was work I started back in 2021, where we started coordinating, co-locating our gliders with these sail drones, these uncrewed surface vehicles. If you can think about it, the gliders collect data that tells us how much heat is in the ocean. These surface vehicles tell us how much heat is moving between the ocean and the atmosphere instantaneously. So you get an idea of both the reservoir and the rates at which the data or at which the heat is moving. And over seasons, we've put them together and had them fly. We've also driven these sail drones into hurricanes, Category 4 and Category 5 hurricanes. This is a sail drone in the eye wall of Hurricane Sam. This is a Category 4 storm. If you've ever wondered what it looks like on the ocean in a Category 4 storm, now you know. You can look away because it is a little nauseating. But this was a really cool highlight of my career to date, is being part of a team. We were all on Zoom together and going, are we in the eye wall? Are we in the eye wall? And then somebody noticed that the measurement called photosynthetically available radiation, which is light, started going up. So it was really super windy, and then the light goes up. We were in the eye, y'all. And it felt like being in the control tower at NASA, jumping up. And, I was by myself at home, like we all were at that stage. But, you wanted to high five and hug and all of this stuff. We've flown into lots of storms over the years and captured features that are not in the model. So we're making the models better in real time. One thing that is pretty common for us is that a storm will start in the Gulf of Mexico and then basically go through Florida. And pop out on the other side like a bad guy in a movie, right? And because the water is so warm on the Atlantic side of Florida, that gives the hurricane the chance to refuel, get stronger, just like the bad guy in the movie, and make a second landfall in our area. So we've had 3 or 4 storms just in the last few years do this. And we position our vehicles on both sides so that if this happens, basically both approaches are covered. If the storm comes from the Atlantic or if it comes through the Pacific or through the Gulf of Mexico. So here is an animation. It's really, really cool. I'm going to play it like 3 times, so don't worry. I'll turn on the little laser pointer and show a few things. So this shows all of the pieces at work during Hurricane Ernesto in 2024. This is a hurricane that moved through the tropical Atlantic, slammed into Puerto Rico, and then glanced off of Bermuda and continued north. So in it, you'll see the storm forming. You'll see the eye here, and then there are little cartoony things of all of the stuff that are in that collect observations: gliders, sail drones, dropsons, aircraft. This is a coordination of all of these people collecting data of one storm. So there's the hurricane hunters doing their patterns and dropping dropsons, collecting point-wise observations. We try to collect those over our instrumentation so that you have both the measurement at the surface and all the way above. And if you're lucky, there's a glider nearby getting all the way down, which is pretty cool. Here you see it go past a sail drone. We'll zoom in. Here's more aircraft going through. That's a drone that they deployed that did basically a spiral pattern on top of it. More sail drones. More gliders. That was a glider from Bermuda called Jack. There have been gliders through this at the start of this, but we've gotten to the point now where the glider data and the sail drone data is explicitly mentioned in the National Hurricane Center forecast advisories. So when you get to that part of hurricane season where you're not just looking at the graphics and you're reading the discussion, and suddenly you have real feelings about like shear and winds aloft and things like that, you'll look and potentially see that the forecast has been revised because of data from gliders and sail drones. You want me to play it one more time? That's the end of my kind of prepared content. I wanted to, like I said, I've got some cool videos, so I wanted to show you the videos. So I didn't want to make it complete chat city. But I wanted to open up the floor to y'all to see what you're most interested in and want to talk about.
Yeah, we'll open it up to the audience. We'll turn these off first.
Okay. Take off.
Okay, can you do the overhead?
So what's the funding look like for this current year?
It's rough out there. It's rough out there. The one thing that really benefits us is that by being a volunteer program for so many years, we know how to show it, and we have just made operations, and good response to hurricanes is not a political issue. This is a safety, protecting lives and property, and it's core to the mission of NOAA. So we are very popular. It's also cool because it's robots, so that helps us in our favor. But in general, it is rough out there. The funding climate is pretty difficult for this kind of work right now on a scientific level. This funds our operations, you know, but that's not the whole story. It's what improves the forecast for tonight, right? But it's not what improves the model for next year.
So I assume there's, I don't know, 20, 50 parameters that go into the model to determine path and velocity. But is there a simple relationship between path and the temperature sinks, or the speed and I don't know, whatever?
Yeah, so the ocean and atmospheric models run as physics-based models. So they start with partial differential equations for the velocity at each depth level, for the surface, for the wind, for all of these temperature, salinity, humidity, all of these things. And so those get solved. It's very computationally expensive. And there's a step that integrates the data called data assimilation that kind of moves it to truth from observations. And so having more observations, especially in these critical places, makes it easier to nudge it to the truth. Right now, there's some movement to see how AI-based models might be able to predict some features of hurricanes. And there's some promise in that because it's super lightweight. However, you have to take real care with that because there's no guarantee that the results will conform to the rules of physics. The other caveat is that these AI models are trained on the past. And so being trained on the past doesn't necessarily help you predict the future if that's not part of your training data set. So I think there's a lot of interest in figuring out how to best combine these things and maybe use AI models to identify trends that are difficult or obscured by the physical data.
So the glider temperature is just a small part of all that.
It's a small part of it, but the ocean heat is one of the two main factors. So the two main factors for hurricane intensity are ocean heat, how much fuel you got, right? And then the other is what's ripping apart the hurricane, and that's the wind shear. So the more the winds aloft are different from the surface winds, that's going to take the column of air, the rising warm air that's moving up that makes it such a nice tight pie, and turn it over, and that's going to rip it apart.
And what's going to affect the path?
It could, but this is for intensity.
What affects the path?
What affects the path? The largest things, as far as I'm aware, are steering currents, these larger atmospheric patterns that move. You know, you see the weather forecast and you see the lines and the L's and the H's move over. Those are going to basically give space for the hurricanes to move around in.
Thank you.
Yes, you mentioned vehicles and things like that. I was wondering, how do you get those to the location, and how do you determine how many to put in at the time and where you put them?
That's a really good question. So we started off by saying, can we do it? And how do you get them to where they need to be is an important question, because when we started this in 2018, you know, we were like, oh, well, let's get one out before the hurricane comes. So we put one out, you know, the day before it became unsafe to go offshore, and the same thing with the one in North Carolina. But if you've heard the saying, you don't have to get ready if you stay ready. So if you have the gliders in these important features all the time, you've already preconditioned the model to be right. You're not trying to fix it at the last minute, and you're able to have gotten the longer forecast that makes the next forecast even better. So that's a big part of it. And the way we identify these places is thinking about these essential ocean features. Where are the big reservoirs of heat, right? That's how much fuel is available. The other big part of it, because some of our water off of our coast is fairly shallow, it's really hot, but it's pretty shallow. So you integrate that and it's not as much as it might be if it's in a deeper place. The Gulf Stream off of our coast is such a big determinant of everything in the ocean and in weather that getting that feature right by getting the edges of it is hugely important for both the atmospheric and the ocean forecasts.
How many do you typically use, one or more?
Well, right now, so this season, we are funded to have 150 days of vehicles in water. So that is 5 30-day deployments is how we typically operate them. Sometimes it's more or less depending on different factors. We have a decision to make. Do we have one in all the time? Or do we try to weight it to the heavier part of hurricanes this season? And normally that's what we do. We normally try to have our largest concentration of vehicles in August and September. In October, storms still come. You all may remember Matthew from 2016. I remember those trees on my house. But things get less predictable then. So we often try to concentrate them in those months just because that's the most action. But back to that idea of staying ready. You're not going to get as good of a forecast in August if you haven't started improving the forecast in July. So this year we have tried to start our hurricane season a bit earlier. As Dory can report, she's been on the boat for every single one of these attempts and all of their recoveries. We've had some mayhem because our gliders are little drama queens who have had hardware failures and required a lot of work in the lab. And Dory has been super helpful and cheery despite our failures. But we're planning to deploy one again next week. And we hope to have at least one glider in water through at least October 15th.
So do you launch them from boats? Do you?
From small boats. Yeah, we have vessels here. We also work with a lot of charter partners. I'll include them here. Latitude 31 dive charters. They're our best friends in the world right now. Their bank account loves us. But we work with a lot of different charters here in the Savannah area. And we use our own Skidaway vessels to get offshore as well, both our small boats and then occasionally we're able to coordinate our efforts with cruises that are already planned on our research vessel, the RV Savannah, which provides sort of at that point, if you can get a free ride, I'll take it.
So do you launch them from the boat a certain way or do you drop them in or what's the?
You plop them in, you let them deploy them off of a rail and they glide off into the ocean. There's a testing period where they come up to the surface and they call home and you're like, okay, can you turn on, can you feel your hands and your fingers and that kind of stuff. And then we send it offline. They are about the size of a person. They're about 5.5 feet long, about that big around, 130 pounds. So 2 people can move them. They're on carts. When they're full of water, 2 strong people can move them. No, but yeah, they're meant to be deployed. Just for size comparisons, I think I did show this in here. So here's our gliders. That's like 5.5 feet long. 130 pounds, this big around. For reference, they cost about $300,000. The sail drones are much larger. They wouldn't fit in this room. They look like big surfboards. This year, we're really excited because we're going to deploy these miniature sailboats, and they look like, if you ever sailed like an Optimist or a Pram, they look like little dinky dinghies, right? They're about the size between me and Jackson. And he and I could pick them up together and throw them over the side. And we've flown those into the eye of our Category 5 last summer. And then we'll have a third kind this year that has a propeller-based solution. So, we started with just the sail drones and have decided in the last couple of years to diversify the kind of fleet we can use so that we've got multiple methods of propulsion. We've got different kinds of vehicles to use, and we're not putting all of our eggs in one basket.
Do you provide the same data to the American models as you do the European models, or Okay,
Everybody gets everything.
okay. And then the difference between the models must be in their calculations or that type of thing?
Exactly. They're all based on the same physics, but they have different assumptions, or sometimes different resolutions. Some of them could say, I want to calculate it every 5 kilometers. Others have different schemes for how to represent those terms. But, you know, there are some parts of science where the data is super secret and you don't share it with anybody until you published it. That's not us. Part of our funding involves the use and impact of the data. So one of the metrics of our success is that people are using it. People are using it and that it has an impact on people's lives.
You mentioned one of the applications of the glider was the tracking of endangered species. Could you give a kind of a high level, what's that?
Sure, yeah. So off of our coast, critically endangered North Atlantic right whales who spend most of their lives in New England and Canadian waters, living their best lives. The pregnant mothers swim down by themselves to give birth. They give live birth because they're mammals off of the Georgia and Florida coast. And they don't eat while they're down here. They're an obligate predator of a zooplankton that only lives far to the north. So they give birth here, they nurse the calf until it's large enough and strong enough for the two of them to run the gauntlet back. So they're threatened by entanglement by fishing on lobster pots and things like that. That's mostly north of North Carolina. But in our part of the world, what endangers these animals most is ship strikes. So that's why we have a seasonal management area and seasonal management zone where ships of a certain size are meant to slow down to keep an eye out for any animals in the area. So they are hard to find and there's not a lot of, they're being quiet because they don't want to be spotted, right? These are babies, moms and babies together. They're not going to be super flashy. So they're really susceptible to vessel strikes. So on our gliders, we put basically an underwater microphone that listens for the sounds of animals. And there's a library on it that listening in real time compares the sound it hears to the digital signal of different kinds of whales. It identifies it, says, that's a North Atlantic right whale. So when it comes up again, it can say, hi, my name is Angus, and I heard a whale. And that data are verified by analysts on shore, and those get shared through national and international networks in the same way that the hurricane data are. And those ultimately go out as a VHF broadcast to mariners that a whale has been spotted. So that's our other main, we go back and forth lately between hurricane season and whale season.
Do you do that in the non-hurricane season for the most part?
Essentially, yeah, they're down here. They start moving from the north in November. They make it to our area in December, and then they normally start heading back in March and early April.
Perfect.
Who has developed these devices? Universities, government, private enterprise?
So for gliders, I'll start with them. This started as an idea by a guy named Douglas Webb, who, and actually before that, it was Henry Stommel, who's kind of one of the great grandfathers of physics of the Earth. And he said, well, what if you could just change your buoyancy and move that way instead of like having to use propellers and stuff like that? That would be cool. And in the mid-90s, the Office of Naval Research basically put the idea out to bid. Here's this idea. I want to get 3 or 4 companies to bid on it and make me different models. And of that set, 3 companies emerged. 2 were based at universities, one at University of California at San Diego, another University of Washington, and then a private company based in Falmouth on Cape Cod. Each developed, they're slightly different from each other. They've got slightly different characteristics and outshine each other in different areas, but those are the major manufacturers that exist now, starting with that federal seed funding. We use the company out of Massachusetts because they have gliders that can operate in the shallow areas where we do our work. The sail drones and USVs are a more recent invention. So they too started as seed money being available for autonomous things. I'll say with some humility that these kinds of projects help build these companies, right? That through NOAA funding, most of this is federal funding through NOAA. Sail Drone was able to, and Ocean Now and these other companies were able to start with prototypes, put the sensors on that we need, fly them into hurricanes and show it could be done. So that fueled future development into the company. So in that way, it's really a public partnership. And one other interesting thing about them is that these USVs have moved to a bit of a data service model. Instead of me buying a glider and running it and doing all of it and maintaining it and fixing it and all of this stuff. With these technologies, you can buy one of these guys, the little ocean guys, but by and large, for these missions, we buy the data as a service from the companies. And there's advantages to that. They assume more of the risk, but then they also say no to things you want to do as a scientist, or they have the ability to change some things, and so there's some advantages to either model. But that's a fairly recent invention, is this idea as you're not buying an instrument, you're buying the data. You never owned the instrument at all. You just have to trust us that we did it right scientifically. And that we'll do what you tell us to.
So most of these look very fragile, and hurricanes are pretty tough. So do you track the loss of how many and things like that?
I try not to dwell on these things. But gliders are surprisingly resilient because they're not perfectly safe. They're fairly safe underwater. They're flying around, they're minding their own business. The most dangerous place for a glider to be is at the surface. So we try to minimize the time at the surface for a lot of reasons. One, because it's dangerous. You could get hit by a ship, you could get attacked by a shark, you could get attacked by a turtle. We had that happen too. You could have a fisherman pick you up and drag you home. So it's suddenly going 20 knots toward the marina. We've had that happen too. We've had lots of different combinations of things happen, but bad things happen at the surface. It's expensive to send data, so we try to limit our time at the surface to the most essential data we can send in real time and make your decisions as fast as possible. So that time at the surface is also where the waves are going to slap you around. So while the gliders when a hurricane is going over or when you have a big storm, you adapt the flight of the glider a little bit. We raise it a little bit more from the bottom so that if it happens to be at the bottom, when a wave comes over, it's not going to slam into the bottom. We sometimes will have it not surface as regularly while the storm is happening because the hurricane forecast is going to be what it is, whether I give you the data now or in 2 hours when it's calmer. And then sometimes there can be damage to the fin. The one externally moving part of the glider is the fin that determines where it goes. And that can kind of get beat up at the surface by waves, but so far so good on those. So we have lost gliders. We've lost 2 to sharks. We've had all kinds of non-fatal damage as well. Claw marks of sharks. We have dental material embedded into the tail of a glider that got attacked by a shark off of Cape Hatteras. We had bite marks from a giant waterhead turtle that had been messing with it. And we've had gliders be sunk by remora fish that try to suck up onto the glider.
So how does the glider tend to interact with other parts of the environment?
So, interesting. I've just done a permit application for Grays Reef National Marine Sanctuary, so I had to think a lot about these things. Like, what is the worst thing a glider could do to Grays Reef, or to the ocean around it? So if most of the time the glider's flying through, it's very quiet because it doesn't have propellers. So it's not making noises that would scare things off. I think there's some interest by some modeling. What's that doing over there? But in a planned mission, the glider comes home with everything it came in. So we're able to say that there is very little to no environmental impact by the gliders when they're deployed. The gliders don't take physical samples. All the sensors just sort of stick out into the flow or listen into the flow. So we're not leaving anything behind or bringing it with us. We do get some interaction. We get some biofouling by these remoras that suck up onto us, and sometimes some phytoplankton that grow on us, or barnacles, if you spend a lot of time at the surface, can start accumulating. But we try to stay low impact, no impact. We can.
And how long are they out there? If you deploy one, how long does it stay out?
They stay out for normally, so let me back up. Beep, beep, beep. So the glider moves every time it changes its buoyancy and center of gravity. It moves each of its motors. So if you're in super shallow, super deep water, you move it once, and then a long time later, you move it back and you've moved a long distance, right? But if you're in shallow water, you have to keep moving, right? And so that's a lot more inflection, and it's a lot more motion. It's a lot more power used. So they get a lot less efficient if you're in shallow water. So on our regular rechargeable lithium batteries, we get about 30 days in shallow water. On those same batteries, if we were operating in deep water, we'd probably get 45, 60 days, somewhere in there. They also make non-rechargeable single-use lithium batteries that can, for a deep water, like the ones we deployed last week, glider operating in its simplest mode, they can stay out for 5 to 6 months. So those provide a lot of bang for your buck. Those are the ones that we send out into the very deep water in the Sargasso Sea, the large pools of warm water there.
I'll ask one question. So we are approaching the height of hurricane season right now. So what are you excited about or focused on right now as we go into that?
Right now, we're focused on getting a working glider in the water. That's like goal number one. We're probably going to be doing that in the next week or so. So look at our social media for when it happens. You'll see big smiles and happy yellow gliders. But the other thing I'm super excited about is, in prior years, we'd only used one kind of surface vehicle at a time. This year, we've got 3 different kinds. So the first few years, we operated only sail drones. Last year, we operated only ocean, the smaller, less expensive ones, and they proved that they can handle it. So what I'm really thrilled about is in the next few weeks, I'm going to receive a big package with 2 of these things in it. And we're going to build them here with help from the company and deploy them from Skidaway vehicles offshore. So that you will 100% see on social media as soon as it happens. Some of our technicians and one of our undergraduates who is a part-time technician is coming in town. He's an engineering major at Washington and Lee, and he's going to be one of the technicians working on that. So that's what I'm super excited about this year, for sure.
And then one last question for you. So you do a lot of work with right whale monitoring when it is not hurricane season. But does this work continue, or is there importance of this work when it is not hurricane season?
Oh, absolutely. The whether there's a whale or a hurricane coming, either way, what we're doing is sampling in areas that are essential for getting the forecast of the ocean and the atmosphere right. So living on the coast, it's easy for us to see how the ocean affects our everyday weather, right? The reason it rains in Hardyville every time I'm on 995 in Hardyville, it's raining, driving north out of town, get a big dump on you. That's often sea breeze driven thunderstorms that are forced by the ocean, right? Anytime you get a winter storm, they come down and they interact with the warm water of the Gulf Stream, and that strengthens them and tilts them and causes bad weather for us on our coast, causes dangerous winter. And we talk a lot to people, to lawmakers about why it's important. You know, if you're in Iowa, then you're like, well, I don't care if it's raining on I-95, right? But I bet you do care if your Amazon package got there, right? Or if your estimate for your package got right. And the weather forecast for the Port of Savannah and for the roads, for the truckers to take to get all of the logistics there for all of this stuff we do in a modern society, those all have underpinnings of ocean forecasts and weather forecasts and getting them right. The insurance industry also really cares about this state because they care about the risk for the assets that they insure. So it's a big part of that world as well.
Are there any other questions out there?
In the time that you've been doing this, have y'all been able to document like a rising temperature of the ocean?
Yeah, it's hard to see because there's so much variability year to year. And, you know, one year the Altamaha flooded the place where we sample every year and it's super, super fresh. I think if you look over longer time periods, you see some fairly strong evidence of warming over those longer time periods. How that affects hurricanes and our ability to sample through them is an interesting question. Just like if you've got training data sets that are based on the past, it's hard to predict what the next step in the future will be. We think about that a lot. A lot of our climatologies that the weather forecasts default to, if you don't have gliders flying around getting you data, same thing in the atmosphere or the ocean. If you don't have something giving you real data, often it defaults to an average or a climatology that was based on data collected over a number of years. You know, the climatology that I depend on for winds in the South Atlantic Bight is based on data from the 40s, 50s, and early 60s. Similarly, if you look at the data that the glider collect and you compare it to climatologies of temperature and salinity, we started to be able to do this by going to a repeat section off of Georgia over the last several years. And we can see over a season what's happening, the evolution of the density field. But we can also compare to those climatologies and we can see how much of a departure is this from a normal July. And one of the things I'd really be interested in doing is taking all of this wealth of data that's so much easier to collect now than it was in the 40s, 50s, and 60s, and seeing if or how some of those averages might have shifted. You know, some of it may be due to climate, but some of it also happens because you're collecting more data. You're seeing a wider range of conditions that you can see with autonomous sensors. You don't have to wait for good weather to collect data with a glider, but you did on a ship in the 80s. So that can kind of shift some of those averages as well.
So is the ocean less variable because of such a large mass that can absorb heat, as opposed to, I mean, the last 10 years in the United States, the temperature records are broken every day, constant tornadoes, 100-year rainstorms with 5 inches of rain an hour. I mean, those are unheard of things. That's all happening on land, but it's not happening in the ocean.
Are we measuring it as much in the ocean? We see a lot on the land, right? We
Okay.
see it, we observe it. We're all kind of amateur weather people, right? Because it matters to us if it's raining, if you're driving to work or going shopping or going to the park, going to the farmer's market, right? It matters to you, so you pay attention to it. If you really pay attention to the weather offshore or in the salinity in the Gulf Stream. So it's harder to measure, it's harder to see. And I think these are exactly the technologies that'll help address some of this.
All right, let's give a hand to Dr.